So anyway, I'll be talking about what the title says. One fun side note, apparently if I move my mouse, it will call out that I used ChatGPT to help edit the graphic, even though I then modified it in Illustrator. So I love that they keep you on your toes. Don't use generative AI and not face it. Okay. So the motivation for today is going to be, I guess, I would say that for this project, almost like I tried very hard to be less celestial. And then in the end, we're going to come back around and realize that we have a celestial-like construction. So celestial holography for me means flat holography, and then also a bit of an emphasis on asymptotic symmetries. And so the research program that I guess all of Andy's students came out of was really trying to milk that notion of the asymptotic symmetries of asymptotically flat spacetimes being much larger than those of the naive thing you'd think in flat space, or the analog if you came over from ADS. So, well, I guess a lot of the talks that we've seen that were more in the celestial side of things have kind of two approaches. So those students, the colleagues of mine who came out of Harvard, focus a lot on a bottom-up approach, this infrared triangle of understanding the connections between soft theorems, asymptotic symmetries, and memory effects, then treating that like a 2D CFT and getting from the OPs the celestial currents. And then the Simons collaboration came out of really seeing how those symmetry algebras coming from this 2D treatment, those OPEs, tied to a top-down construction that matched the chiral algebra. So Natalie and Kevin coming in, finding a particular example of a top-down construction that was maybe some strange flat space where you had the same symmetries. And so that's a lovely, I guess, full circle moment where you can go from the bottom up, basically try to say, let me assume that whatever hologram I have on the boundary has these ingredients, and then find a top-down construction with it. But at the same time, the price you're paying is that these top-down constructions are a bit weird and they're not what we're used to. So for the spirit of this talk, or at least this research project, was me begging Rob to help me learn more about ADS CFT and various fun things you can do there. So I guess one downside of learning through one research program is that for me, everything I was doing was already in flat. And so when people would make comments about, well, like flat holography doesn't make sense or whatnot, I wouldn't even appreciate the context in that, because you can sit in on Sheehan's course, but that doesn't mean that you fully appreciate the things you're not actually working on. So the goal of the project is the following. So we're going to play around with what goes wrong when we take the flat limit. And then I'm going to avoid needing to know a lot of string theory. But apparently, there should be, like you can see how much work David was putting into trying to find other top-down models and make the gravity more like just self-dual gravity instead of full Einstein gravity. So various problems you could have there, trying to understand when you take a flat limit, do you still have this decoupling, or do you have now your ADS is not the same ADS space like it's coming flat, but instead this whole ADS S5 cross S5 is now your flat space. But I'm going to focus more on the bottom-up approach because, again, we were all in we grew up playing with asymptotic symmetries, and so that seems closest to me. And so we're going to do bottom-up ADS CFT and play around with some ideas. So this is going to be work in progress with awesome grad student, Jackie Caminetti, and Rob Myers. And I want to quote the references that I'm mainly basing my talk on, which are going to be papers by Bagchi, Grumeller, and collaborators on a BMS field theory entanglement entropies. The title of the talk is about a swing surface proposal that came out of work by Wei Song and collaborators. And then the thing where I'm actually going to do a computation that I guess is new will be in connection with these work by Hijano and friends. And so as much as, again, I'm going to frame the talk as like, look at these fun things we're learning. It's a kind of wild west of flat space holography and ideas out there. I want to point out that Wei Song is here, so is Bagchi. So we can have fun discussions if you are willing to ask me as many questions as I've asked you guys. Great. OK, so this is the roadmap for the talk. Every time you see this slide, so I'll have it every time, I assume that I'm asking you if you have any questions, and pause me if you want. The first thing we'll look at is bottom-up ADS CFT. Good. And I feel like it's finally getting quieter when the doors open. OK, so what do I mean by bottom-up ADS CFT? Framing the question of, like, let's do for understand how what we do for flat space holography fits into similar ideas in ADS-CFT. The thing that I guess all the celestial folks have put a lot of time into is this notion of matching symmetries, and the fact that for a flat space, that symmetry structure is a bit richer than we might have expected just from taking the flat limit. And this is particularly the case when I'm talking about, say, 4D, where I wouldn't have expected the isometries of my ADS4 to have these super translations and super rotations, but you've heard from Anna last year and in other papers that she's worked on trying to understand how to get these currents that we have from soft physics from ADS. The second thing that I guess was the motivation or having fun exploring in these ongoing work with Rob Myers is kind of the other aspect of this kind of bottom-up structure. And I won't be able to do the same justice that Raphael gave at the beginning of his talk, where he's setting up all of the kind of surprises of what he would frame as geometry telling you. And so I feel like if we want to understand flat holography, you know, the asymptotic symmetries are important, but there's this kind of level right above understanding the kinematics, more related to understanding also like causal structure in the boundary and causal structure in the bulk, and which regions of the boundary encode which regions of the bulk, that we really haven't played as much with, at least as the celestial holography community. But lovely enough, there have been a lot of work, I guess, by other people in like the Carrollian literature, a little bit away from what we do, that have tried to ask these questions, and that's what we're going to play with in this talk. So for ignoring flat space for now, the point would be that if we understand how semi-classical bulk geometry is encoded in the boundary, we get some fun, deep insights into the connection between quantum information theory and quantum gravity, and wouldn't it be lovely if we could exploit that or see how that arises in our flat hologram? So that's going to be motivation. So for the grad students in the audience, and I guess because we don't have a teaching requirement perimeter, so me just trying to practice how to give some background, Ryu-Takayanagi tell us that if we are, like, say, in a CFT, and I take a region of my boundary, and I trace out what is going on outside of that region, the von Neumann entropy of that reduced density matrix is going to be equivalent to some minimal or extremal surface that is homologous to that boundary region. And so for the purpose of this talk, I'm going to stick to 3D for reasons that you'll see later. And in that case, I just have some interval on my boundary CFT and some geodesic as my RT surface candidate. And then just because these equations will appear later on, let's look at the length of this geodesic versus this entanglement entropy. So I have my ADS. For this picture, I'm just drawing an equal time cut. I put some cutoff at a very large radius, and I measure the length of that geodesic between the cutoff surface. I get some quantity, and lo and behold, if I had instead been on my CFT, tried to compute the entanglement entropy by the Renyi entropies, I would find that I could instead like replace my this replica with a correlation function of twist operators, which are primaries with some specific dimension, and I can use that to get to an entanglement entropy where up to matching the UV cutoff of the CFT and IR cutoff in the bulk geometry, I have a match. And again, this match is consistent with Brown and Hanau's analysis of what the central extension would be for the Virasoro symmetry that I have in ADS. Great, okay, so now all I want to say is that if I was just in Einstein gravity, I would have Virasoro symmetry where the left and right central charges are equal, and it's 3 ADS scale over 2 G Newton. And at the same time, I'm going to also introduce very briefly, but just at the level of I care about it, the symmetry algebra, that if I was instead in topologically massive gravity, I have this extra Chern-Simons term, and now I have central extensions that are different left and right moving central charges. And so that mu parameter there, if it goes to infinity, I go back to my standard Einstein gravity, will shift the relative values of the left and right central charges. And so just because this will rear its head inadvertently later on in the talk, if I had now had an interval that's not an equal time, then I would have my entropy being a sum of a left and right moving term. Alejandro Castro, Iqbal, and friends have been studying those entanglement entropies, and I've written it in a manner where I'm kind of introducing periodic coordinates on the cylinder, and then in this tau coordinate would be compact if I hadn't unwound that ADS time. So, okay. Now back to that motivation slide about bottom-up ADS-CFT. not only do we have this RT formula, so everything I'm going to be talking about for the majority of the rest of the talk is related to an RT proposal in flat space. But again, to remind ourselves of what it's good for is that like Wall and others have helped us understand the extent to which I can reconstruct everything that's within that wedge defined by that extremal surface and the conformal boundary where I have this domain of dependence in the boundary. And so ideas like that are what actually motivate why we're having fun doing what we're doing in this talk, because later we're going to want to understand, even though it won't be in the scope of this talk, how to talk about regions on the conformal boundary of flat space-time and reconstruct the bulk. But I won't be able to get to things like that because we're still learning about it. Okay. Yes, please. Perfect. Exactly. Time for questions. It gets modified, no. So in that context, you have some Wilson line computation that you can do to match it. So that's where I pointed. Yeah.
Okay. And then do you see this this anomaly that
So the central charges are different as anomaly, and this, I think you're going to see that these expressions don't quite look like Lorentz covariant the same way in the boundary. So, but the reason why I write that term down is just because of something auxiliary that's going to happen in this literature where like you could just co-opt answers with these left and right central charges that are different. But for most of what I'm doing, I really want to think of the bulk being physically just Einstein gravity. Yeah. Any other questions?
Bulk reconstruction, if I understand correctly, refers to when you have a CFT and you try to build a bulk.
Yes.
So is there anything that tells me if I start with a CFT, whether it'll have a flat space dual in the bulk or a ADS dual?
So, I mean, I would have said that most of what we're, okay, for example, like the notion of when the CFT is holographic, there's some constraints on like the values of the central charge, for example, but that's still built up into intuition from the ADS context. The problem that I would have in flat space is, first of all, like when people ask, what's the central charge of celestial holography, or things like for example, I would have said that like even in this flat space context, we'll see this, the Penrose diagram obviously has like null infinity. And so I wouldn't even know if it makes sense to, if I have this Lorentzian CFT, like view it as like being a time-like surface that you're attaching now to flat space. I think like the asymptotic structure is just different. So like where the CFT would live would be one way for me to be scared of trying to say something in that direction. I don't know if that's a satisfactory answer, but like I definitely like would not just try to think that if I had a CFT that's like normal unitary on a cylinder, that I would say that there's some conditions where it would be a flat thing. I think that there is a sense in which I'm doing computations in normal ADS CFT, and there are going to be some quantities that are going to limit to nice flat space answers, and that's what I'll play with more. Good? Okay. Great. So now we're going to play with flat space times, which is, I guess, so we know better. So for example, for Penrose diagram, which is, I guess I've lied a little bit. I've actually like shown you the angular direction, but I'm going to be talking about 3D flat space today, and so throw away all that soft graviton-like story, but you actually have a nice, richer symmetry structure that you can relate to ADS, which is nice, that we'll come to soon. And all I want to say is that for me, if I'm interested in thinking about a theory living on the boundary, perhaps the most natural boundary, just from staring at this diagram, is going to be the one that is Carrollian. So my future null infinity, I get to by keeping U fixed and going out to large R, and that's the metric for flat space. But obviously, there's a larger class of asymptotically flat metrics that will have a different metric. So now, what do I want to say here? I basically want to point out that if I'm looking at different geodesics, the ones that are actually going to make it out to null infinity are going to be these null geodesics. And so you can already kind of see a kind of tension or confusion of if I tried to think of like this usual RT formula, where I have my conformal boundary, I have some interval on that conformal boundary, and then I want to look for some geodesic between those endpoints. They were spaced like in the simplest example I was talking about, and now what do I do when I'm trying to do the exact same function built up from flat space, and I'm stuck with the fact that the geodesics that are actually going to make it out to the conformal boundary are going to be null. So I could just put a screen, and then maybe I'd be fine, but it's already something a little bit different. Okay, and so let's just point out a couple other things about taking this flat limit. So first, I'm going to make a nice change of coordinates, and that's discussed in this lambda BMS paper is where I grabbed that from, of Compare et al. But this notion of trying to see how to get massless scattering from ADS CFT correlators has been studied by a variety of authors. I guess like Polchinski and Panadonis have had work on that. But I think for the way that I'm writing it, the closest references would be Hijano, and then the paper was by Leonardo and Anna. So I do this coordinate transformation, and so now I see written instead of the time coordinate, this retarded time u, and in particular, I can ask different questions. So if I take this metric and I just send my ADS scale to infinity, I get back the flat metric I had on the previous slide, versus if I instead had said, let me send r to infinity first, then the cute thing that I see is that this ADS scale is appearing here. The parts of the flat metric that didn't have any r squared out front are subdominant. And so that leading metric in that large R limit looks like just a cylinder, which I would have expected in ADS because I am in ADS right now. But then I can subsequently think about taking that flat limit, and it looks like the speed of light in that metric is being sent to 0. And so that's a sense in which there is naturally this Carrollian theory that we think of as living in some band of my ADS spacetime. And so just to remind you why Carrollian is weird. And so I guess the timeline of the papers that we're using from this Carrollian or Galilean CFT literature is similar to when this soft physics program started. And you can see the trade-off in a couple of ideas. So definitely some of the talks at the BHI would have been, let's just study innovator contractions of my symmetry algebras on their own, and that's great. And then talk about Carrollian CFTs or other fun things you can do. Galilean CFTs, for example, and their own right. But then you might say, why the hell are you doing that? My speed of light is 1, relativity is awesome. Now, from the point of view that we're saying here, we see naturally that if I'm talking about some flat limit, then I want to have my boundary be null. And so it makes sense as I limit towards flat that I am sending that speed of light on the boundary to 0. But so on the one hand, if you wanted to say, I'm always going to design things so that I am matching to something in the bulk, you get people complaining that, well, how much do you actually know about this hologram? You're just building it from the bulk out when the bulk is semi-classical and perturbative. And on the other hand, you're going to find that in the Carrollian literature, there's a lot of results that maybe you don't know what to make sense of, and that's what we're going to be playing with today. So Carrollian, my light cone squishes up, and it's as if I'm basically zooming in on that little time band. Galilean versus Carrollian, you can think of rescaling the x versus time coordinate, and it's like my light cone squishes down. So ultra-relativistic on the last slide, non-relativistic on this side. I'm not going to say much about Galilean except for in as much as you'll see some co-opting of Galilean limits to Carrollian limits to do some tricks to match computations people wanted. Okay, so the next thing I want to point out is, of course, that that people actually know how to get to a BMS algebra from the Virasoro symmetry you have in ADS3 CFT2. And that's great because now you have non-trivial central extensions. You have the soft physics, not at the level of soft gravitons, but instead more like the Bonney mass and angular momentum aspect. And it's the infinite dimensional symmetry algebra. So things look great. And so if anything, flat space 3D has all the structure that it feels like you can just take from ADS down to your flat space story. And so why not play with that? The thing that I want to point out, though, is that there's some subtleties with the fact that the generators that are the natural combinations to get you your super translations and your super rotations have this funny mixing of the positive and negative modding on the left versus right movers. And that's what's going to cause some of the subtleties in this Carrollian literature, trying to tie it back to flat space hologram. And so, fine, I can take those linear combinations, and when I do take those linear combinations, say, of the vector fields, I see that there's no ADS scale sitting around anywhere here. And so I have what looks obviously like super translations or super rotations, and I got my BMS3. And at the same time, the nice thing I had with that contraction is that my central charges have no ADS scale in them either. So I have my C left and CL and CM, which CL would go to 0 if I was just back in Einstein gravity, which is the one I care about more. And CM is 3 over G, so it's dimension full, which is consistent with the algebra because we rescaled those translation generators by a length scale. But at the same time, it's also not manifestly divergent in the ADS scale when we're sending it out to infinity. So that's the nice thing about it. Oh, yes. So, like, I think that I would point to, I don't know if it's Donné or compare others. I think people have tried to talk about interbiddle matching in the context of, like, the 4D case, at least. In this story, I am, like, not even going there at all. But to be fair, I think that the way Romain and Laura would have talked about interbiddle matching was, like, forcing it. Because if they're just talking about a theory living on this null cylinder, then there's another copy of the null cylinder. They're going to impose the antipodal matching as like a boundary condition on that Carrollian theory, rather than seeing it from the bulk. But I also think that that's a separate question than maybe Anna has looked at the bulk and ADS and seeing if there's antipodal matching too. But I'm not going to. There. Yeah.
Does this contraction trick work in higher dimensions? Because the CFT3, the algebra is finite dimensional. Are you going to get BMS4 out of that?
So that's the thing. So you don't get the BMS4 from the contraction of the global generators in ADS, but you can get the global part, right? So like the fact that I can get back Poincare from the ADS isometries works. But the issue is that I think, so that already points to a slightly different nature of the kind of extra symmetry enhancements in the higher D case versus in the 3D case. So in this case, I told you, you had the Virasoro symmetry, now you have it. I think that Anna and friends would tell you that when they're trying to get those symmetry generators from ADS, there's a funny order of limits where there's some extra symmetries you get because you're looking at correlators only in that little time band. But it's not like obvious to me like how I would get, yeah, if that answers your question or not. Like, I'm saying that it's different.
Mm-hmm. So 3 dimensions is special.
3 dimensions is definitely special. And then I would assume that the thing that makes kind of, okay, so every higher D you expect to have super translation still. And then I think 4 dimensions is also special because you have these super rotations, but all of these guys are coming from some stress tensor correlators near that U=0 cut and some prescription for how to take the flat limit of that, which seems like they were able to get it from stress tensor ward identities, which makes it seem like it's still somehow there in the parent ADS theory. But definitely the role doesn't seem to be the same, but maybe Anna can say more there. So, okay, yeah. Yes.
Of this algebra BMS4?
So I would be scared of, so the Cordova-Shao story is very much as if I'm in the bulk though, and I'm treating the theory like it's free in that, I mean, the sense of like, I wouldn't have, Cordova and Shao is in the same dimension as the symmetry algebra that they have, which is slightly different than the picture here, right? We're gonna encounter light ray operators as something interesting for us here, but it's a little different because it's not like a long scry. And then also, yeah, so I think if I was trying to relate Cordova-Shao's story to the BMS algebra story, then I would be in the bulk, but probably in the bulk near the conformal boundary and hoping that the region near the conformal boundary is like free enough that it's like a CFT, and then I have those realizations of the stress tensors near the boundary, more like the hard charges in the story still. So I think that it's fair enough, but it's still, okay. So one thing you could say, which would be, let me be in higher D, let me be on a light sheet, hope that that light sheet is near my conformal boundary, which I wouldn't have normally had before I took the flat limit, and then build these like stress tensor moments and have an algebra, and I could do that. But I still think there's probably a disconnect between doing that which is strictly built from a CFT on a null sheet versus from like the limit where the region, the boundary becomes like the full flat space. Yeah, sorry.
Well,
Yeah.
I think it's not so hard to get the W symmetry from the deformed W symmetry for ADS.
I know you're working on it. Do you got it yet?
No.
Sorry, like you're talking about Skinner and the.
Yeah.
Okay.
Augsburg group yeah.
Fine.
I'm sorry.
Okay. So the question was just about getting, like there's a deformed W infinity that they're able to study in ADS CFD, or understanding like certain operators that would modify the algebra when you're in ADS. So Yeah, I'm not, first of all, I'm also not even talking about W infinity here. I'm talking about the global, like the leading and subleading soft theorem analog. But to be fair, to the extent that you can generate those from stress tensors possibly on the boundary, it'd be a relevant question, but I'm going to avoid that for now. Any other questions? Good, okay, I shall proceed. Okay, so basically the thing that I want to point out now is we're going to go back to this question of understanding what regions on the boundary are going to be dual, or be what I want to kind of associate to various regions of the bulk. What's the RT prescription for an extremal surface that would measure the entanglement entropy of that region? And so we already kind of see that we could be scared again, that when I'm taking this flat limit, because I have this kind of ultra locality property of my Carrollian theory, I basically should be a bit scared that like it's just vertical, like my light cones become these like straight lines. What am I going to do about that? Is it going to run into some problems for me about different regions on that boundary? So now let's go through a bit of a fun overview of those papers that I was mentioning before. So for this next part of the talk, it's all going to be about playing with the results of Bakshi, Miller and collaborators, Wei Song and collaborators, and then connecting it back at the end. And then a lot of the statements that are conclusions about those papers will still be under construction, work in progress. And so if you fight me on it and we disagree, I'll incorporate that in what we actually write up. So basically, the first thing I want to say is that imagine someone handed you a proposal for the entanglement entropy for this interval of null infinity. And that's exactly what Bakshi and Grumeller did. They would have said in their paper that if I have a BMS field theory living at null infinity, and I look at an interval of size delta u and delta phi, that the thing that I want to say is the entanglement entropy would be this quantity. And so now what I want to do is I want to focus on the case where the RT proposal is valid. I don't have any funny corrections because I have a theory with like C left and C right being different. So I throw away the first term. That first term is the one that we saw on the previous slide that looked like the usual geodesic up to just suppressing the cutoff here. And what I would get then is that they would claim that the entanglement entropy is this delta u cotangent delta phi. And that's a bit weird. But in a very fun or like maybe surprising way, Wei Song and collaborators were able to find a bulk quantity that was equal to that. And so the prescription that they had was motivated by kind of following the procedure of like Cassini, Huerta, and Myers, where you're looking at basically vector fields that preserve the endpoints and then trying to map that to some black hole geometry to read off the entanglement entropies. But for now, I'm just going to describe the prescription that gives you that length. And the game is as follows. So I have my interval on null infinity. I take the endpoints. I shoot in some radial geodesics. Now I want to think of a surface that's going to basically be tied to either of those two fixed ropes. And I'm going to vary along those two endpoints and find an extremal curve. And then the minimal length one is going to be, well, in this case, there's only one that's extremal, equal to that value. And so they have a prescription where there is literally some piecewise geodesic that ties out to that boundary interval whose length is equal to this quoted entanglement entropy. And so that's fun, but it's also just very different from what we would have in the RT proposal. And so for the sake of my artistic skills being bad unless I use ChatGPT, in which case I get called out, this is the image from Wei Song, where we have this swing seat whose length is going to be equal to that quantity, and these ropes that are these very specific null geodesics that are radial. So it looks like a swing, so it's called a swing. Now, again, for the purposes of this talk, the point is this, let's learn how to use this. It's very different than the RT proposal, and so we're going to be playing with that. And like basically the goal of the rest of the talk is just have fun with it. Basically, that's the problem. So I would say that like it's a larger class than vacuum. So it's anything where it's like locally vacuum that they're able to do this maps. So it's single interval in like various like thermal or black hole or like defect geometries I think they have answers for. But again, it's, yeah. To be fair though, I would have said that the reason why, like, we'll see in the end that when I'm playing with this, it's more to kind of appreciate this kind of disconnect between different parts of this flat space holography literature, and then also try to find what other physical quantities are really living in that flat space region near the center of ADS that I can play with. So I'd say that's a bigger takeaway than like thinking like, does this proposal even make sense as a thing that I want to like die on? Oh, that's like a sword I fall on. Good. Okay. So again, if we think about what I was saying before about the fact that I thought we understood how to take this flat limit from this bulk point configuration, then there'd be a different geodesic sitting out there, which would have been this RT surface that literally goes between those two endpoints. Now, one problem you could run into is that those twist operators, we wrote down their conformal dimensions, they're very heavy, and if I was in flat space, I wouldn't even want to think about putting these massive operators out at extrapolating them out to null infinity. So on the one hand, basically, by sticking to flat space and solving for which, modular flows were well-defined in flat space, they ended up only on, like, say, the spatial modular flows, which I'll show in a couple slides later. But basically, the thing right now is there's these two candidate surfaces. One of them is RT surface that I have. The other one happens to be equal to this quoted BMS field theory entanglement entropy. So what's going on? So on the one hand, so where did this BMS field theory entanglement entropy come from? And I think it boils down to some choices being made that I would be sympathetic to the extent of trying to engineer something that is manifestly finite in the ADS scale. So the problem that they have is when you take this Carrollian limit, where I had those little dragons and was pointing to some subscripts, is that if I think of the state in the theory as being a Virasoro primary before I took the flat limit, then I would see that if I took that flat limit, I wouldn't have a representation like that is a BMS primary, which is the one that they wanted or they were assuming. Instead, I would basically have the modding here being different and some rest frame primary condition. So it really boils down to, I guess, an assumption on the representations of these twist operators when they're doing their computation. If I had instead chosen to flip all of, say, the right-moving modes, then that primary condition would land on a BMS primary. And so whether it's a historical accident or just the fact they're motivated by Galilean field theories, you have this contraction, you have these central charges. If you do a computation in the Galilean contraction and you get a value for the entanglement entropy there, and then you think that it's a function just of the central charges, you would get that quantity that they had for the entanglement entropy. So just to be clear, we have this Carrollian contraction, which we had before, this mixing of the left and right moddings, and we had a Galilean contraction. And then you have central charges that would be different in these two. So in the first case, we had no ADS scale appearing in the central charges on the right-hand side. If we had done a contraction like this, we would have different values of the central charges. One would be divergent in the ADS scale. And then you'd also see that the generators, if I just took those linear combinations, would not have a nice flat limit. So there's motivation from the point of view of literally matching to the BMS symmetries of that flat space of taking the linear combination above. But the trick that they're playing is just, let me try to, if I try to say that my twist operator correlators, I am matching to some expectation of, say, the left and the right stress tensors on this multi-sheeted Riemann surface, then I can do my computation using the other contraction where the Virasoro primaries are limiting to my BMS primaries, and then just swap out the central charges. And so that's the reason why I was alluding to what are the values for these expressions if I happen to have TMG, because there's a sense in which their auxiliary space-time where they're doing these computations would be topologically massive gravity. So that's the game that they're playing when they land on this quantity for the BMS field theory entanglement entropy, where they kill the CL term and CM term because of that choice. And so, fine. But let's think a little bit about whether we had to do that or not. So this Galilean versus Carrollian statement is coming from the fact that if I was trying to think about taking the L bars and sending them to L negative bar, then what I would have is basically an inversion in that Z bar coordinate, and that roughly is flipping my time and space direction. So you can see that that operation is Galilean versus Carrollian is roughly rescaling time versus space differently. Now at the same time, if I actually want to think about my twist operator sitting on some cut near tau is pi over 2, then what am I doing? I'm not actually putting my operator at the origin of my complex plane, which is supposed to prepare the state in the cylinder. Instead, I'm doing some SL2C transformation to move that operator around. And when I do that, nothing tells me that that SL2C transformation can't have some ADS scale dependence in it. And so in particular, when I do that conjugation, then I take a flat limit of those quantities. It's much more like a Galilean contraction. And so that's great because at least it tells us that I could have just taken these twist operators in this ADS CFT, found a flat limit where it makes sense that I would be reproducing the original RT proposal in ADS, with the caveat that, of course, now it's divergent in the ADS scale. So that little aside there is something that if like Arjun's around, I'll talk to him about, like that ability to do a slightly different contraction when I'm talking about reproducing entanglement entropies. But at the same time now, let's unpack what that would mean for us for the swing surface proposal. So for the one contraction, we would get C left to 0, and we just get the swing surface bench. And then for the other contraction, I'm getting the usual RT proposal. Great. So any questions at that point? No. Good. So now we get to have fun. So I would have said that at the stage before, you could say that the kind of takeaway is that there's a lot of fun to be had by going through the other flat holography literature, precisely because of the fact that like the one downside of celestial is often we're building things up from the bulk. I mean, like the kind of forced results are in the context of seeing, if we have soft gravitons in the bulk, we have these symmetries, da, da, da. But then you're a little bit worried about how much of the boundary theory I'm actually able to define that way. The Carrollian literature has a much more brute force approach, I'd say. Like there are elements of it where I'm just looking at Carrollian representations of the Carrollian algebras more abstractly, but at the same time you run into this kind of funny things where if you had somehow wanted to not have any ADS scale, you might have thought it made sense to assume these representations where you had BMS primaries, and then you'd run into some troubles if you then try to match it back to the bulk. So I think there's a lot of fun to be had just playing with it. Now, for the rest of the talk, I want to basically be saying fun things that you can do when you try to just see why are all these things working, even if I might not necessarily agree with the starting point of saying that that's an entanglement entropy. And so the first thing to point out, and I'll probably go through it rather quickly because in the interest of time, is just that, at least for the case of being in global ADS, you can have a nice interpretation of that quantity that they do run into. And roughly, if we understand how they got to that swing proposal, you can see that they basically are just swapping the left and right moving parts to have a space-like modular flow is the one that they're looking at rather than a time-like one. So what that means in the end is that roughly the quantity that they have would be swapping out the relative sign of the left and right terms, which you can think of as measuring, instead of the modular Hamiltonian, like a difference between the left and right guys. And in particular, more of an accident, it does have an interpretation as a mutual information. So I don't want to spend too much time on it because I think that this is something that's just an accident of the global case, but it's also fun because, say you're reading some papers by Alex May on mutual informations and scattering, and then you see that that surface is a swing surface, you get to then dive into a whole bunch of literature. So it's a lot of fun. Basically, the thing that I want to make just very briefly is that for the case of global ADS, that little swing surface segment happens to be equal to a mutual information of the null intervals that you would, or nearly null intervals if I regulate them, kind of that are defined in terms of, say, the causal diamond on the boundary. So that's all fun. But the other thing that's more fun, I think, is that so many things kind of came out miraculously from just this equation that someone proposed. So imagine you're given some entanglement entropy proposal for this BMS field theory computed nominally from the CFT side. You might be scared about strong set additivity, where are absolute values in that quantity, et cetera, but then you find that there's a bulk dual equal to that. So that already points to wanting to basically better understand what is this bulk quantity. That's a bulk quantity I could lift to ADS. That will be a lot of the next part of the talk. But then even beyond that, Hijano and collaborators were able to say, let's look at the swing surface. How does that swing surface reproduce that bench? Can I do an analog of my ADS geodesic Witten diagrams for flat space and reproduce these BMS correlators? So there's kind of a lot of things that worked, even if your starting assumption might be something you could debate with. And the goal of this talk is, again, to have fun, explore these things, and push it through. So roughly in these papers with Ramdu, Hijano and collaborators, we're looking at a claim that they could reproduce these correlators of BMS primaries from spearing bulk operators along some radial null geodesics in flat space. And so we're just going to look at that dictionary and lift it up to ADS, because I can just as well define these radial ones in ADS. So the goal for the next part of the talk is to do what the title says, which is let me lift these swing surfaces to ADS. And when I say that, I mean I'm lifting both those ropes to ADS and then that bench, seeing why the bench comes out. So the maybe more concrete computational goal is let me try to find what boundary operator would correspond to an operator speared along a bulk light ray. Now, one way to do it, which then you run into a bunch of I-epsilon prescriptions and you have to read like Tom Hartman's paper on the stress tensor analog of it, is For a local operator, I have HKLL, so let me just take that and smear it along the light ray. I'm going to try to cheat and do an easier thing, which I'll say at the bottom. But I do want to point out that there is some precedent where you might think that you know what you're supposed to do, to the extent that if I thought of that guy as the limit of a space like geodesic, then I might have thought that if I have an operator smeared along the geodesic, it's like one of the ingredients of my geodesic Witten diagrams, and there's an OP block interpretation of, say, which of that exchange particle is integrated along a geodesic. So we're going to have something kind of fun in the null limit that is a bit different, I'd say, than the space-like case. And the way that we're going to do it is this kind of cheat trick, which is a lot of assumptions built in. So I'm going to basically follow the way that Hiroshi and Nakayama had derived HKLL just from symmetry constraints. So basically what I'm doing is I'm just going to say my state is going to be prepared by some single operator that's just a single particle operator on my vacuum ADS, and then there's some kernel that is going to be smeared along on the boundary that's also just prepared from the operator it's dual to, and then I want to try to find what smearing would match the symmetries of how that bulk local operator transformed. And so there's a lot of assumptions and restrictions built into that, but again, it's a fun, informative thing. So the name of the game is as follows. I'm going to start with my scalar field. My scalar field is going to be just smeared along some null geodesic. And in particular, I want to keep track of the fact that why is radial special? I know that if I have, say, if I'm in global ADS and I just shoot out all the light rays, there's a whole light sheet I could have been on. And so in particular, when I'm in a 3D bulk, I have this angular momentum of those light rays, or equivalently an impact parameter for how far away I am from the ADS origin, that I should keep track of. So let's do that. In embedding space, I have then that coordinate, the value of x, which is like my angular momentum or the transverse kind of impact parameter of that geodesic, as well as the time I'm going to be integrating along that null ray. So when I play that game, the next thing I want to do is I want to pick a nice basis where my L0 and my L1s fix the point u equals phi equals 0. And so I have that, and I can write that nicely in terms of the generators of my embedding space, which then I also know how to take the flat limit of. So in particular, I'm introducing light cone coordinates for x0 and x1. The embedding space generators go from -1 to 2. And the translations are going to be that flat limit or contraction of the j nu -1. So when I play this game, some fun things happen. The first thing is that I do see, and so this is again kind of validating why did Hijano accidentally have these null radial bulk null geodesics in his dictionary when he was trying to match to the swing surface proposal, trying to match to computing these BMS field theory correlators. And that's because you can see that the generators that would be L1 and L bar 1 are such that you're literally turning into a total derivative along that light ray. And so you're annihilated by that. Nice. You also see that if I look at the thing that is the dilatations, that roughly I have now a boost that would be like t d by dt along that light ray. And so by integrating with parts, I get that that dimension is 1. And now, so that gives me the first claim, which is that this guy has definite weight and is highest weight. Now I can use that and just use the dispersion relation I get from the Casimir. So because it's a primary, so that L1 and L bar 1 condition, then I have that it should reduce to the mass squared times the ADS scale squared is the standard formula for the spin and the dimension, but I know what the dimension is, and so I get that the spin is related to the mass in this funny way. But I also don't get a definite value of the spin, I just get the spin squared. And that might be a bad thing, but it's actually a good thing for the following thing we'll see later. The first thing I should point out, though, is once I see those values of the dimension, I already kind of have, I guess, a green flag, or I want to say, it reminds me of something I know from the 2D CFT, and that's the spectrum exactly that I would have for my light transforms. And so, in particular, assuming some assumptions about, being in a state that is built from just a single copy of that boundary dual operator to this bulk field, because I'm in a single particle kind of subspace of my Hilbert space, and then the fact that I have some, control or uniqueness of the various intertwiners, I would now expect that I have a state that should be built from this light ray operator and this light ray bar operator, so the two different ways I could go around the sphere. And these guys have dimension 1 and spin that's plus or minus 1 minus the dimension as a function of the mass. So you're running into this. And in particular, the symmetries alone would tell you that it seems like I should have some linear combination, and that relative linear combination can be made consistent with the fact that it should depend on x. So if we had found instead that it had definite value of the spin, we'd be out of luck to the extent that that should seem inconsistent with the fact that this bulk operator should have some dependence on where I am in the bulk, which light ray I picked. So the superposition changes appropriately, but we can't pick any phases. So at least it's kind of fun that you seem to see that these boundary light ray operators come from this bulk smearing. And those boundary operators are also nice because it's a way for us to have these BMS primaries, so we can see that in that change of frame I was talking about before, I have a primary condition, and I also have definite values of the weights. It's a way to get a very highly spinning primary, such that when I take this flat contraction, it gives me the form of the correlators that I want. So on the one hand, you could have said these twist operators that I guess Bagchi and Grimiller and friends wanted would have been very highly spinning guys from the point of view of this flat space limit of this bulk point configuration. And if I take this large L limit, I indeed get that delta U cotangent phi from it. And so that's one way to view it, but at the same time, I know now that if I wanted to produce a highly spinning operator without being worried about unitarity and things like that, I could have said, let me just have light transform the local primaries that I had. And that's a fun way to basically be talking about then massive fields that are living near U equals phi equals 0 because they're really the light transforms of things that were going around spatial infinity. So basically now, for the rest of the talk, I'm going to be playing with refining this ansatz. Any questions at this point? Okay, so what are we going to do? First thing that we have is we said the symmetries told us, so symmetries, this assumption that I'm in this states produced with a single operator that is single particle operator. Now I want to be able to say that I want to match the 2-point functions as well as some consistency with the fact that I would think that if I go out to very large values of x, that I should reproduce the light ray operator or its light ray bar. So for a minute, I want to go back to flat space and think about how the 2-point function was matched there. So the proposal, again, was that there's this little swing surface that's suspended between these two rays. And it's kind of similar to, not so much to the geodesic Witten diagram story is like it's supposed to be exact. So it's like I've solved for the same Casimir equations, and I have that I can just get the same answer by integrating my interactions along the geodesic. The thing that then I get if I take like a semi-classical limit is sometimes those exchanges are dominated by the minimal length geodesic, say, between those curves. So it's a step more like that. And so we're going to try to see in the flat space case exactly how that little bench length comes about. And the easiest way to do it is you just go to momentum space, and then I'm going to do this 2 integrals along those rays. And what I get is the following. So I'm in 3D. That I epsilon prescription doesn't matter in this bulk case. And what I get is that those 2 integrals along those 2 light-like directions localize 2 of the momentum space integrals. And the thing that I'm left with is an integral over the transverse momentum. And then depending on the sign of that separation, so I could have just as well like put the operators in the other direction because it's just where do I put these 2, I would get an absolute value here. Now, to be fair, I'm doing this computation in a very specific bench configuration that isn't related to what I had said before, which was that I wanted to send these radial geodesics going in from the boundary. So this was just for ease of computation, so I don't have to pull around a lot of funny terms in the exponent. But if I had done that and I'd said, let me pick those rays to be the radial ones from given points, then I would again get back the form where in that exponent you're getting that swing bench story, and then this dependence on the angle is consistent with what I was saying, which is that it's delta is 1. Now the problem that I have here is that basically position dependent or the correlator dependent choice of how I close that contour is giving me an absolute value, which is great from the point of view of then having this like positive quantity as a length, but bad from the point of view of just saying that it's a correlator of primaries. So we're going to have a little bit of fun playing around with how to get that absolute value from the ADS CFT uplift that I have. And so what are we going to do? We're going to go a little bit crazy. So the first thing that we do is we want to see what the analog is of if I try to just reproduce that last computation in flat space in ADS. And the easiest way to do that is, now again, I'm probably shoving under the rug some analytic continuations between the Euclidean picture and then going to Lorentzian, but I want to use a split representation of the propagator, and then I have a very similar setup. I can go to a Mellin representation for these p.x's, turn it into the same plane waves I had before, do those 2 integrals now, But instead what they do is they localize me. If I look at the correlator of like light ray smeared guys, they would localize these momentum, which in this case are the boundary position integrals. And then the third integral that I'm left with, where I want the contour prescription to matter to give me that absolute value, would be in the Mellon weight. So it's almost like if I wanted to have my 2-point functions have that absolute value, that I need to have a way to analytically continue that Mellon weight for my operators. So let's just play along with that idea. And this is where it was kind of amusing that something celestial seemed to save the day. So in celestial CFT, if I was doing, say, massive scattering, then I guess with Andy, we had this picture where we're taking the on-shell, like a dagger, say, of a massive single particle operator, and we're using a bulk to boundary propagator for that guy, smeared in some way to give us a primary living in the celestial sphere. So what I could do is I could just take my bulk field, and rather than extrapolate it out to the boundary, which would have given me the standard O with a given dimension, I'm going to try to force myself to have something on the principal series by doing the smearing with the bulk to boundary propagator. And if I do that, then I know that just by various like shadow symmetries of that scalar bulk to boundary propagator, that I should have a linear combination of some operator and possibly its shadow, where the coefficients would be symmetric. And I could, in principle, absorb those coefficients in the definition of the operator if I wanted to, but I'm going to pick a nice choice so that it looks closer to what I would want. So the shadow symmetry is why those coefficients are related. And then if I play various games with completeness relations for just those bulk to boundary propagators in ADS3 for a scalar, then I can invert that equation and write down some ansatz for what the 2-point function should be for these principal series guys, as well as the kernel that I want there, so that I'm basically saying, let me write, or like implicitly define an analytic continuation of my CFT primary to the principal series for these external states to reproduce a bulk field and some of its correlators. So this should be consistent by construction, unless I may have a time mistake somewhere, with the symmetries as well as the 2-point functions, because I was getting it from the split representation of the propagator roughly. And then in particular, if we want to see that if it's consistent with the extrapolate dictionary, the game that I'm playing is just telling myself that, say I look at the extrapolated limit from that kernel there, that's the bulk to boundary propagator. If I take that large, I guess in this case 0 goes to 0 limit, and I'm going off the boundary, then if I close the contour in the right way, I indeed would pick up the pole so that it's the operator back at O delta. So it seems consistent, but at the same time, it's literally like I've engineered an analytic continuation of the external states, conformal dimensions, in order to then just play the trick of trying to get those 2-point functions to work. So if I have that expression and I trust it, I can do the integral along a light ray, and then I get back the thing that I was kind of claiming above, which is a linear combination of the light ray operator and light ray bar, again, because they're related by a shadow transform, so it's consistent with that ansatz of O and then O shadow. And I also have then that there's poles that it picks up, so that linear combination now is kind of contour dependent. So the fun thing is that we've played all these games just to match the 2-point functions, as well as the swing bench would come from those correlators in that limit where it's dominated by like the geodesic between them. So I think we've had fun, and then I would pause here for questions too at this stage, because I've done a lot of things I probably shouldn't have done. Anna. Yeah, yep.
So this is a formula for a field. So phi is a field in ADS or in
So
flat
phi
space?
is a field in ADS, and then almost by definition, I've tried to define these boundary-like operators.
So sorry, but okay, if we go back, the phi should have some dimension, right? Delta, that's related to the mass, but
Exactly.
here you are integrating over
Just a-
C as well. That's the thing I'm a little
Yeah, so C is like a principal series weight, and so what I'm trying to do is find a way to analytically continue the weights to the principal series for the external operators, which I normally wouldn't do. Normally I use like completeness relations, and these principal series are appearing in like the conformal block decomposition, or as like internal things that I then go back, do the integral, have it like localized to poles that are now my physical operators.
So, but when you push phi, sorry, dumb question.
Yeah.
When you push phi to the boundary, you would expect to get back an operator of definite dimension, right? Delta in ADS.
Yeah, and so the game that I would play here is I would get that by the nature of my
Oh,
contour
I see.
prescription.
So then that, when you perform the contour integral, then that would give you,
That's the goal, yeah.
wait, but why doesn't, so that formula does, okay, but that formula you're saying that it gives you the O delta.
It's
sorry.
a choice of coefficients so that this would work, if that makes sense. So I think there's a lot of, I'm happy, like this should get a lot of questions if like,
Okay.
yeah, good?
Thank you.
Anyone else? Because I think that's a weird thing to do, so, yeah. Temple?
Sorry, maybe you missed it. Is there a notion of these surfaces?
So for example, the thing I'm constructing right now, I could lift to higher D. I think I would basically have some like Boltzmann boundary kernel in my, like I guess there's a lower dimensional ADS that is like the Rindler horizon that I would be also smearing over to get it. The question is, there's a bit of a disconnect between, yes, people have claimed that there's a swing surface analog in higher D, again, in like global spacetimes, and whether this construction is relevant to it, because I'm really just sticking to light rays for my rep theory now. So yes, and then also yes for this, but they're not the same yet. I haven't figured out the analog of the swing surface thing here, because it might be it's a different dimensionality.
Are you saying then that your prescription could be generalized to higher dimensions that may not have been appropriately comparing the proposal to surfaces?
So what I'm saying is that I picked a problem to solve that would only be the same as the problem of the swing proposal in the case of 3D bulk. I know how to generalize this light ray bulk operator, I think, to higher D, or at least I thought I did. Maybe I have to double check it. And then separately, I know that Wei Song and friends have had proposals for the swing surfaces in higher D, but that shouldn't be the same, so I don't think I've thought about how to reproduce theirs in higher D.
I see.
Okay.
Thanks.
Yeah. So I want to view it as effectively as an analytic notation of boundary theory, but I would agree that there's a sense in which the fact that I'm defining it in terms of the bulk makes it more natural to kind of... sorry. So if I took a flat space limit of this guy... So I haven't played with it, but I would assume I could try to do the same games that Anna would do, to the extent that, like, especially if I put my bulk operators, say, near the bulk point or out where she would, I could play these games, but I haven't played with that additional step on top of it. But yeah. I don't know. Good. Okay. Any more questions? So let me then get to just the open questions and next steps, so it's good timing, which is the following. So the first claim, or I guess observation, would be that I would have said that the entanglement entropy for this BMS field theory might not be what I would have called an entanglement entropy for this interval that I'm doing as the bulk point configuration that I take that flat limit. However, I can also understand the different inter contractions as just a change of frame. So it's not like I would say, if I look at Barnish's paper, which contraction gives me the BMS algebra and the central extensions. I'm not fighting that. I am basically, I guess, the crux of the difference is coming from kind of the fact that there could be a different BMS subalgebra related by a transformation that would normally not be in the BMS algebra because it's this ADS scale dependent large kind of SL2C transformation from the point of view of the flat limit. The other thing is that this bulk quantity that we have is still an extremal surface, and that lets me lift it up. So we could lift it up to these light ray operator combinations. And in particular, it gave us a way to try to think about massive states as being these light ray operators that are going between the point that I'm used to as being like scry in my bulk point configuration, and it's analog antipodally on paths in infinity, but not antipodal in the sense of like it's the past of scry plus and the future of scry minus, more like antipodally Ingli. The other thing that I have is that just by trying to force myself to get this bench with that absolute value, we had this fun game where some celestial holography came in to save the day as far as rep theory is concerned. And then I would like to say that there's kind of many open questions, and I think that the physics that's interesting is really along slightly different lines. So sure, we have this fun story. We've learned a lot about kind of digging through this literature on RT surfaces in flat space and what we want. But I think that the more interesting question to ask for the physics is, what are these geometric probes of entanglement that are going to be relevant to scattering, or basically things that are going to live naturally in that kind of flat space region? And then also more fun with these principal primaries, because it seems like an interesting thing where I'm taking these external dimensions on the principal series, which is not something I would normally do. So those are fun things. And then the actual concrete next steps, if I wanted to flesh out the things in this talk, I can look at the higher D analog like Simple was asking about both these bulk light ray operators, in addition to the swing prescription, the relation to BMS primaries, et cetera, interpretations of different boundary conditions. Like, do I want to kind of uncover if there was a different way to really interpret that as an entanglement entropy again, given there's a swing proposal for warped ADS? I personally am most excited about connecting to this mutual information, the scattering story of Alex May and friends, where you're seeing not only like this RT prescription, but rather that entanglement is a resource that lets you do scattering experiments that you couldn't do in the bulk, or you can do in the bulk, but you couldn't do in the boundary. And then I think there's a de Sitter picture of this bulk point limit, which would help you kind of gain intuition for attaching to different ways of viewing null infinity instead of as the limit of a time-like boundary to the limit of a space-like boundary, where I am kind of cutting scry slightly different, like viewing it not as equal time cut as my cut, but instead like, yeah. So I think those are all fun things to do, and then let me leave it on that. I'm like basically perfect on timing, so yay.